Thank you. Okay, so this is really the work from Sirikan Sundaresan, who can be here. And we've been working, so he was Nick Feamster's student at Georgia Tech, and we've been working on this for some time. So I got to come to Crete and present the work. So in general, we've been working on this area of home network diagnosis. The internet connectivity is really central to today's home. So if you look at all the statistics, people are more and more watching TV, videos, doing voice, telecommuting, doing everything from their homes. So it's understandable that when things get disrupted, when you have problems, you're going to be very frustrated. As a user, if that's what you get when you're trying to watch a baseball match, I think you'll be probably biting your computer or something similar if that's the kind of things you're seeing. And it's a problem also for the internet service providers, because when problems happen in people's homes, I mean, there's nobody to help them administer those networks. So they just call the providers all constantly, and most providers tell us that most of the time the problem is within the home, is not really in the access. Is this true or not? So that's part of the questions that we're trying to answer here in this work. So the problem, as I was just mentioning, is that the home network itself can disrupt the end-to-end connectivity, your internet connectivity, because Wi-Fi and multiple people sharing the network. And the users, they have no clue. Okay, everybody today, I mean, many of us, and more are getting this Wi-Fi networks into the home, all our devices connecting through that. And most people have no expertise in networking. For us, it's okay. I mean, you probably get lots of calls from people asking you for help too. So you know what I'm talking about for these people in the home. So in this particular paper, the question that we are trying to answer is, if you're looking at, okay, the user traffic coming from the internet, going into the home, is the bottleneck that the user is experiencing, okay, throughput bottleneck, is it within your home or is it in the access link? So is it your provider's fault or is it your fault? Okay, who should be trying to deal with this problem? That's a very simple question. And for now, the work that we've been doing, we're really focusing on downstream traffic, because that's the majority of the traffic. And realistic, the algorithm we have now works in this case. We're still trying to improve it for the upstream case. So what's the approach we took? We are monitoring the traffic at the home gateway, the router here that's connecting your home to your ISP. So that's really nice because it's ideally placed in between your access link and your home Wi-Fi, so you can kind of separate the problems that are happening in each side. And we are doing passive measurements. So we are looking at the traffic that is flowing through this router. So why we would like really to look into the throughput bottlenecks that the user traffic, the user application is experiencing, okay? Instead of just doing perhaps active measurements where we could see which link is more limiting, but not necessarily see what the user traffic is experiencing. Plus, there's no measurement overhead. And when you're measuring over wireless, adding traffic into the wireless can become a problem, okay? So you might be draining the batteries of the devices, and you might be introducing more interference, and you might not really be seeing the real bottlenecks, okay? So that's sort of the approach we took here. So I'm going to just give you an intuition of how the algorithm works, okay, the main algorithm works, and I will let you guys to go and look into the paper for some of the details, or you can ask me as many questions as you like. So what we're trying to detect is the bottleneck in the access or inside the home. So let's imagine here that the bottleneck is in the access link, okay? So if you see the traffic coming through, so Sirikan did this animation, very nice. You guys should really see how nice he worked for this. So you have what you see here is, because the bottleneck is here, my vantage point where I'm doing my measurements, it is seeing the traffic coming, the packets are coming, sort of at the same, like a very smooth rate, okay, because they're coming back to back. They're bottlenecked here, okay? So at the vantage point where I'm measuring, I'm seeing the packets just arriving one after the other. So what the intuition we get here is that if you see the smooth packet arrivals, then it's sort of indicating, in our case, that there is a bottleneck at the access. Remember, looking at downstream traffic, and I'm measuring here in my bottlenecks just before. Okay, so that's sort of the high-level intuition that we're using for building our detector of access-linked bottlenecks. And if you look into some data, so here what we've done controlled experiments where we knew whether the bottleneck was at the access or it was at the wireless. So what these CDFs here are showing, this is the coefficient of variation of packet interarrival times. So that's the metric that we're going to be using for this particular detector. And in this line, these are the cases where the bottleneck was in the access. Okay? So as you can see, the coefficient, so there's not a lot of variance on the packet interarrival times. Okay? Because you get that smoothing effect that I've talked to you before, the packets are arriving back to back. Whereas when the bottleneck's in the wireless, you see that the coefficient of variation is much higher here. So we can kind of separate when the problems are happening in the access or when they are happening at the wireless by using this particular metric. Okay? So that's one detector that we are doing. So the way we are doing this detector, as I said, we have these controlled experiments. So we run a bunch of different cases, and then we are doing likelihood tests to sort of tune the thresholds for the detector. So now let's see what happens when the bottleneck is in the wireless. So remember again, we are measuring at the home router. Okay, so what we can see here, now no longer I'm going to be seeing these packets arriving back to back here because okay, the bottleneck is not at the access anymore. But what I will be able to observe is I can see for TCP traffic, I can see the RTTs inside the home. I can see the packet coming to the devices in the home and going back to, the X coming back to the router. So by computing the RTT in the LAN, I can get an idea of how backed up the wireless within the home is. Okay, so you can measure sort of the buffering delays and the retransmission delays will increase the RTT within the LAN, which I can measure given the vantage point that I have. We are able to measure exactly the RTT within the LAN, so we can see the RTTs that the packets are observing from within the wireless network. Okay, so that's the second detector that we're going to be training. We're doing the same kind of procedure for training it, okay? We do the controlled experiments, and then we can identify the thresholds for this detector. So here, just to give you an example from the results of our controlled experiments, you can see that when it's sort of similar, so here now we have the LAN RTT in the x-axis, and this is the CDF. So when the axis is the bottleneck, you can see that most of the time, you see, it's like 5 milliseconds to 7 milliseconds is the bulk of the measurements. We'd sort of expect, I mean, it's inside a home, okay? You would expect this delay to be very, very short. The wireless is bottleneck, it starts over here. So it's 25 milliseconds, okay? So it goes much higher when the bottleneck's in the wireless, okay? So you can kind of differentiate these two cases based on this metric. So now let me just give you a quick overview of this algorithm. I mean, we had many names for this algorithm in the past. Now it's called HOA for home or access. If you guys have another better name, we'd love to take it because you're not very good for names. Okay, so the first thing we'd have to do in the algorithm, so we're doing packet capture, something similar to TCP dump, okay, in the home router, in the home gateway. And then as soon as we have enough packets per second, so here we're getting a very, very low threshold. We just want to make sure that we have some packets so we can actually compute if there's a bottleneck. Because if there's no traffic, then there is nothing to be bottlenecked, okay? So if there's not enough packets per second, we just say, okay, there's not enough demand, there's no point in running this. If there is, then we're going to do first the test on the access bottleneck, as I explained to you. And after doing all the controlled experiments and doing the training and everything, we identified that 0.8 is a good threshold for the coefficient of variation of the packet in the arrival times. Okay? So if we see that, we see those moved arrivals, then we say, okay, there is a bottleneck at the access. Okay? If we don't see that, then we have to compute the RTT per device within the home. Okay? If there is at least one device that has RTT above 15 milliseconds, which is the threshold we computed for this case, then we say that there is a wireless bottleneck. Okay? So there might be a single device or multiple devices that are bottlenecked at the same time. Okay? So we're going to be doing the wireless bottleneck detection will be per device, because it depends on the device location, etc. Okay? Otherwise, we say, okay, there's no throughput bottleneck at the last mile, because there might be throughput bottleneck someplace else, but that's not what we're measuring. We're trying to see if the throughput bottleneck in the last mile, access or wireless. Okay? So that's the high-level algorithm that we have. And then we deployed this in 2 deployments. So the Bismarck project, the routers that Nick has been working on with Siricon and their group for a long time. So this is the data that we looked in the paper was from 64 homes in 15 countries, and this data was collected during a month in 2013. And this, so I'm talking about tests, because we cannot run this all the time, and this is the kind of things I'm going to talk about to you in the future work, things we're trying to do. But we cannot run this packet capture all the time in the gateway, so we sample. Okay, you run for 10 seconds. Okay, I'm going to get this wrong. I think it's 15 seconds in this case, a test, and 10 seconds in this case, or vice versa. You guys look in the paper for the right number. and that's what I'm calling a test, okay? And that's the time that I'm going to try to do the detection whether there was a bottleneck or not. Okay, so that's the Bismarck. And then we also were lucky to be able to run this in the FCC Seminoles deployment for the Measuring Broadband America in the US. And there we had over 2,000 homes. And that was only, of course, in the US. And we got it running for a couple of days only, because it's sort of a heavy loaded, means a lot of work for the routers to run. And in this case, we have 73,000 tests. So we were able to run this detection for like over 2,000 homes. And this is, I think, the most interesting plot. So that's the one I want to talk about from this data. So here's for the FCC deployment, because that's where we have more access links. So what we did here was that we binned the homes according to their downstream throughput. Okay, so from 0 to 10, they're in the first bin. From 10 to 20 megabits per second, they're in the second bin. Okay, so you can kind of see, depending on the capacity of the access link, how they would fall. And here is the fraction of the tests with last mile bottlenecks. Okay, from the ones we detected that there was a last mile bottleneck, whether they were in the access or in the wireless. Okay, so you can see with no surprise that if you have less than 10 megabits per second of downstream throughput, you're going to get most of your bottlenecks going to be on the access link, okay, because your access link is limited. Okay, but as you start going above 20, you can see this plot is mostly blue. So most of the time, the access bottlenecks is actually happening within your home wireless. And that's interesting. I mean, you might be asking yourselves what kind of wireless network you have in these boxes. So these are N, and they should be able to the physical rates to be able to go up to 130, which means that, I mean, in the labs we're getting 80, 90 megabits per second with these boxes, okay? So there is something going on when you put them in the wild that's making them limited at much lower rates. So when the ISPs complain to us that most of the time people are calling because they're having problem in the wireless in their homes, maybe it's not that unlikely. Maybe that's really what's going on, and there's something that we should be doing here. Okay, so that's what I have in terms of the main results here. So when we looked, I remember I told you that we have results per device within the home. So we looked at all the instances where we had more than one device at the same time, and we detected bottlenecks. And sort of like half of the time we saw bottlenecks in all devices simultaneously, then half of the time it was only one device. So it means that sometimes it's simply the access point that's badly placed, or there's some really bad interference that's interfering with everybody. And sometimes just one device that's in a bad location, okay? So that's most of the results we had. I just wanted to summarize the findings for us. So we saw access bottlenecks are prevalent when the throughput is less than 10 megabits per second. And when the throughput is more than 20, then you saw the plot is mostly blue. So mostly the wireless becomes the bottleneck. And that's what I was just telling you, that so if it's equally likely to have a single device experiencing a problem versus all of the devices within the home. Now some of the next steps, some of the things that we have been working on. So I'd like to improve the detection algorithm. There are a number of things that assumptions that we had here that I really didn't explain that maybe we should discuss now. So for this interarrival timing property that we use for detecting access bottlenecks, it will work, for instance, for DSL links. And links there you have this sort of constant bit rate assumption and FIFO routers, okay? In practice, that's not always going to be the case. Okay, so for the data on the FCC, we were able to validate because we had the some nodes throughput tests. So we were able to check, for instance, like when we detected an access bottleneck, that the rate, just the data rate we were seeing in the box, was very close to the capacity test that some nodes was getting. Okay, so we were able to validate that somehow, and I'm pretty confident in that plot that I showed you. But I think that moving forward, we need to have better algorithms that sort of eliminate some of these simplifying assumptions. Okay, and these simplifying assumptions also that makes it hard for us to do anything upstream detection, because in the home we have wireless. So these things, you know, especially assuming the constant bit rate, it's not going to work for wireless. Okay, so these are the kinds of things that we would like to improve so we can detect both upstream and downstream bottlenecks, and we can detect bottlenecks for a wider variety of access links. Another problem that we had, I mentioned briefly, is that we needed to do sampling because doing the per packet capture will overload the routers. So we've identified some issues with the routers, especially the computation of the RTT. It really kills the routers. So we are having trouble really making this implementation run online. Our current implementation, we are sort of exporting the PCAPs and doing a lot of the computation on the servers, okay? We'd like really to move this to the box so that you don't have to send any data out. Even for privacy reasons, it's always complicated to push this data out. So it would be much nicer if you can just run this within the box. And we are getting lots of interest from ISPs in general because they have this claim that they often have problems within the people's home. Like if they have something like this, it can really help them in the discussion with their customers. Okay, so that's what I had for this. I just want to, one last thing. I figured I'm in a measurement conference, I needed to do some publicity. So we are starting a MOOC on internet measurements with my colleague Timur Friedman. Isn't this France Université Numérique? It's a French MOOC platform, and we are doing the MOOC in English. So we need help advertising it from people here who think, so it starts in May. And it's, of course, completely free, completely open. So for those who are interested, please help us advertise as widely as possible. Thank you.
All right, so before we move to questions, first of all, I forgot to introduce Renata properly, but any one of us who spent any time in measurements probably know her work very well. Anyway, Renata Teixeira is the senior researcher at Inria, where she spent many years, more than 10 years, I think.
Inria just for 2013, but I've been in France for a long time.
Anyway, any questions from the audience? I have plenty of questions.
Okay. Yeah, go ahead. I can use this one for now. I don't need to move anymore.
Hello. The large RTTs for the wireless bottleneck, do you think that's rate adaptation going to the slowest rates? Is that the part of why?
So, okay, we have a hard time with the FCC data for the wireless because we couldn't get the radio taps for in the FCC. In the Bismarck, so we had a PAM paper last year, I think it was last year, where we discussed a little bit some of the wireless issues we were seeing in the Bismarck deployment, where we could get radio tap headers, so we could see whether there was retransmissions, we could see the file rates, so we were able to correlate the RTTs with those wireless metrics, okay? But for FCC, the only thing we can know is whether the access point was using G or N, and we were looking into that a little bit, but in many of the cases where there was a wireless bottleneck, the AP was using N, and we don't have more information than this. So that's a part of the things that in the newer versions, the newer version of the algorithm that we're trying to work on, we're trying also to see whether we can get more information from the driver for helping us in answering these questions, because I think that the next question is, if we have the problem really within the home, then we need to help these people. Okay, what's happening? So why is that happening? And we're really working on that now as well.
Thank you. Imagine a home with 3 teenage kids which constantly watch Netflix or listen to music, and perhaps the home also has voice over IP phone. Now, my question is, would your algorithm be sensitive to this type of traffic? It could, in principle, generate false positives and signal a bottleneck link in the access part, because the traffic is smooth by nature.
So if you have 3 kids watching Netflix, probably the access will be the bottleneck, no? Because they will be trying to use up a lot of the access capacity. I mean, I don't know which, in your scenario, which capacity you're saying, but I don't. So this smoothness that we are talking about, of having really the packets arriving back to back, I don't see how that could happen if the access was not a bottleneck. Because if you have different streams, it's very unlikely that you would get exactly the packets arriving back to back. But I agree with you in the sense that I don't love this metric. That's why I'm trying to get a new one that's a better one, especially because it's not going to work for all types of access links. You know, like if you can imagine a crazy case, for instance, that just the packet sizes. Like if you have alternate packet sizes where you have very large packets and very small packets alternating, and even if the access was bottlenecked, you would think that the inter-arrivals are changing because of the size. So this metric, there is something that's not fully there yet, you know? And that's what we're trying to work on.
So you said that one of the problems is that running this stuff on the CP is you know, IS people usually like to do that. I try to do that a lot in Telefonica, and they don't let me run anything. But one thing they're doing is virtualizing the CP. So now they're running in the cloud, which is usually at the Tesla. So I was wondering if you could extend this to run in such a scenario, and for what you need as a support from the home, because you need some access on layer 2, I'm assuming. So.
Yeah, so the problem of running this away from the AP, perhaps some of these you'll be able to do, but I think that the main issue really is like what I was just answering when Daryl was asking his questions, that we want more visibility into the wireless, and that you need to be in AP to get. Okay, so you could run some of the intelligence away. That's what we're doing now, because we're running it on a server. Okay, we're just getting the data and then running it on a server. But I think you really need.
And that's the heavy part that you have.
No, the heavy part, like some of the RTT computation, these things it's done on the server because we're just exporting it. And then we have a little implementation that's running online, but it's heavy. It works in some like small, you know, I can do a demo of it, but it's not going to work because when the traffic starts to go high, then the problems start arriving, and then you know, we start dropping lots of packets, and you might impact the performance of the user. So that's part of the things we're thinking about now as we are extending to do the online version of this algorithm is, can we go away from looking at the packets? You know, can we, because the routers, they already export number of statistics. Like if we change the metrics we are using, we might be able to do something that's lighter weight and get pretty close to what we are doing now. So I don't have an answer, a full answer because I don't yet have a full solution. I have ideas, but I don't have a full solution yet. Yeah.
Thank you.
Okay, perhaps one last question over there.
You mentioned in the beginning of your presentation that when you're not seeing a smooth inter-arrival times, these are signs of bottlenecks. How do you differentiate this from buffer blow indications?
So the buffer blow tool will usually be in your home router. So you'll mostly be experiencing it in your upstream traffic. We are looking at downstream traffic, but in general, the buffer bloat will be increasing the RTT, and we are looking at the inter-arrival time between two packets. You see, so perhaps packet 1 will be experiencing buffer bloat and packet 2 will be experiencing buffer bloat. So they both have high RTTs, but the delay between them will be the size of the packets if they're queuing, you see. So it wouldn't really change the metrics we're using here, even if it was on the bloat was before the access link.
Maybe I'll take sort of my prerogative as a session chair and ask you another question. So on the broadcast style access links like cable modems, wouldn't you sometimes see the jitter of the packets arriving your way because of the competing packets going elsewhere?
So that's part of the problem that I was telling you, that this doesn't work for all the access links. So we did, because in the FCC, in the US, there are lots of cable networks, okay, and we validated it in cable networks. And for the ones we tested, of them, it worked okay. Like when we are to the lower speeds, but when you start going to higher speeds, these kinds of problems arise a lot.
And that's exactly
and
where
then
you see
we
this
wouldn't,
interesting.
then we wouldn't be able to get the right guess it right. So that's why I was telling you that I think we need better metrics. So for me, the main value here, the main takeaway you should is like that plot that I showed you. I think that's correct and that's interesting. The first time we get this kind of statistics, okay, is this algorithm the final answer? No, I think we can do much better. Yeah.
Well,
Okay, thank you.